Hi, and welcome back to the Low Level Devil channel's OS development using the Linux kernel series. If you haven't seen the rest of the videos in this series, check the comments section for the playlist. In a previous video we went over the break system call, which shows how the end of the application's heap memory is modified. This is useful for us to grab more memory for the application, but in order to use this effectively, we need to create a memory allocator. Essentially, we need to create an implementation of malloc and free. That's what we're going to do in this video. There's quite a bit of code here, so I'm going to try to go through it very quickly. And so if you have any questions or if you need more details, feel free to add comments in the comment section or join the Low Level Devil sub in Reddit, also linked in this description. So let's get started. First, in order to make this memory allocator more efficient, we're going to use the mmap and munmap syscalls. We'll look at the manual here. This has the arguments for them, and this is for mapping files to memory sections, but we can also use it to map anonymous sections memory. So we're just going to copy this and put it in our code down here. Let's see, I'll put this in our include file. Let me rename these to sysmap and sysmunmap. I'll put these in our header as well, make them extern. And essentially, whenever we have a large section of memory, we're going to use the mmap instead of the heap, which is what the malloc does as it is now. So I'm just going to put these fields in order. And munmap just takes the address that you're unmapping and the length of it. And I'll show how this is used in more detail in later. Right now, if you remember in our util, we have this memalloc function. We're just going to get rid of it, and we're going to create a completely new file here called mem.c. Include our headers, include printf for some debugging. So now I'm going to make some defines. First, if I want to debug this, I'm going to have a little flag here to print out some details. So let's see, next I'm going to add a comment here to explain how this memory is set up. So what we're going to do is allocate chunks with the S break, and a chunk is going to consist of a header, which is 4 bytes, which has a size section with its 29 bits, 8-bit aligned, and flags at the end of it, which are the last 3 bits. So a heap chunk is going to consist of a header, the data section in size, and then a header at the bottom as well, which essentially makes a doubly linked list. For mmap, we don't really need a doubly linked list, so we're just going to use the header at the front, just like this. So here's a little, and the header flags, first of all, are going to be, bit 0 is going to be the allocated flag, so if it's 0, it's free. If it's 1, it's allocated. Bit 1 is just going to be a bit that helps us know if it's mapped or if it's on the heap. And bit 2 we're not using yet, so for now it's reserved. So to give an idea what the heap is going to look like here, imagine this here is the start of the heap, and the very first chunk as well. So this first 4 bytes is going to be the size and the flags, followed by a bunch of data sections, followed again by a copy of that header, and then the next ones will start. So we'll have the header section for the next chunk. So yeah, this here is the first chunk's header end, and this here is the second chunk's header begin, and then the second chunk's header end, and it would be eventually followed by the end of the heap, which would be the current break value. So now I'm going to create a bunch of utility functions here just to make the code a little bit simpler and easier to read. I'm going to add some flags as well. So the mem allocated flag is going to be 1, and the flag for mapped is going to be 2. Page size is going to be 4K. Our resize threshold is going to be 16. I'll go over that a little bit later. The mmap threshold is going to be 128K, so if it's over 128K, we'll use mmap. The size of a header again is 4 bytes. The full header size is, of course we have 2 headers, so it's going to be 8 bytes. So then we're going to have the header size mask, which is going to be how we mask the actual size from that header value, which is everything but the last 3 bits. And the header flags mask is going to be the last 3 bits. And hopefully you understand how bit manipulation works. If not, leave some comments and I can describe a little further. So now we're going to start with some pointers. First we're going to have the heap start. Everything's going to be set to null at first. So then we'll have the first free section, and then we'll have the end of the heap. So these are the 3 pointers that we're going to be keeping track of. And we'll create a simple define just to cast one of these pointers to a 32-bit pointer so that we can dereference it to get the value, for instance, the size value from the header. So now I'll create a function to get a chunk size for a pointer. And we're just going to return the dereference 32-bit value ANDed with that header mask so that we just get the bytes that are related to the header size. We'll create a isAlloc, which will return true if it's allocated. So we're just again going to dereference the header and AND it with the mem allocated flag. And we'll have isChunked map for the mapped as well. And I'll also create a isChunk free, which will essentially just return is it not allocated, just a convenience function. Alright, so now going to create another convenient function to get the next chunk. So if we have this chunk, we know we just got to go add the chunk size plus the full header size, which is 2 of the headers. That'll give us the next chunk. And then chunk set size, which we're going to want to set the value on the start and end header. So the start one is simple enough. We just dereference it and set its size. For the end one, we want to do p plus size plus the header size. And it's complaining here. Actually, we're also going to return the pointer too, just to make it simple so we can call this function and get the pointer back in case we want to make another call on it. And we'll say chunk set flags as well, which will have 32 flags. And in this one we're just going to or equal it with the flags. Or equal it with the flags. And it's still complaining. What is it complaining for? Let's see. We'll have an unset as well. And for unset, of course, we're just going to use and equals not flags. Okay, I think I see, because this size field is not there. So what we want to do, instead of calling size, we'll call chunk size p. Alright. So now on to the next one. We have line 8. So this function, we're going to pass in a size and it's going to align it to 8-bit. What we're essentially going to do is we're going to grab the flags from it. If the flags are set, then what we want to do is add 8 and then subtract the flags. Otherwise, we're going to just return the size. Again, if you're confused about how that works, just leave comments or join the subreddit and I'll explain. So now we're going to initialize the heap. We want to set the start point to the sysbreak. And we're going to initially create a page of memory for it. So we'll call sysbreak again with the page, with the start plus size. So now we're going to set the first free section of memory, which is going to be the heap start. And nothing's allocated yet, so let's set the size to the full size of it. So the size of this first allocated section is going to be the page size minus the headers. Remember, we don't want to include that header size in our size in case they need that exact amount of memory. So now we'll have some debugging information just to print out some details like where the heap starts. Heap start. We'll put the end and some other variables here. And we'll put the size of the first chunk and the size of the full heap. Now for this %L to work, I'd actually make a fix to the printf code. So I'll show you where that's at here. In printf, this ULI2A, we just need to change that D variable to unsigned long int. If you missed that, just go ahead and pause it. I'm trying to speed up the video, otherwise it's going to take an hour to go over this. So we'll have a print heap function. If we're not debugging, just return immediately. If the heap isn't initialized, we'll initialize the heap. And what we're going to do here is print out the heap's location, start and end, and its size. And then we're going to simply loop through the linked list of chunks. And we're going to print out each of them. Print out the location and size of them. So first we start with the heap start. While it's less than the heap end, we're going to call p equals next chunk. And now we're just going to print out the details of that chunk. That's the address, the size, and whether it's allocated or not. So there's the address, the size, and a little, is chunk free? Then we'll say free, otherwise alloc. Okay. So now we can, let's put P in there, yep. Now we can get started with the rest of it. So we're going to start with finding the first fit. So we're going to allocate a size. We want to find the first allocated, or already allocated block that'll fit in it. So we're going to loop through each of the blocks, starting with the first one that's free. If that chunk is free and the chunk size is greater than or equal to the size that we need, then we'll return that chunk. Otherwise, we'll return null, which means we need to allocate some more memory using the sysbreak. So now let's call the allocate new memory function. So when that does happen, we're going to first grab the number of pages that it would take to get that size. So we're going to do the in size divided by the page size plus 1. So now we want to see if the remainder is less than the size of the full header. If so, then we allocated enough for the data, but we need more space for the headers, so we'll just add an extra page. So now we're going to say the size is the number of pages times page size. And now we simply want to say our previous end is the current heap end, and the new heap end is now sysbreak plus the heap end plus size. So now we're going to return chunk set size. We're setting the size and also returning the pointer. That's, remember, our convenience function here. So we're setting it to the size minus the full header size. So now comes our malloc implementation. So this is where the user passes in the size they want. If the heap's not allocated or created, then we're going to initialize it. So if this in size is greater than the mmap threshold, we're not going to use the heap, we're just going to use mmap instead. So what we're going to do is just call the sysmap. We give it null for the address. We need to give it the size. Then we have these prot flags, which is read and write. And the flags are private and anonymous to be able to use it as just a pure memory section. And -1 for, anonymous is complaining, but it's actually seen. This is just my IDE issue. It's there. But -1 is for the file descriptor. So since it's not an actual file, we use -1, and it'll create an anonymous section of it. Now we're going to set that size and set the flags to flag mem mapped on there and flag allocated. And then we can just return that location plus the header size, because the the user's pointer starts just past the header. Now next, we're going to 8-bit align this size. So if this is going on, it's not going on unmap, it's going to go on the heap. So we want to make sure we're 8-bit aligning this. First we just 8-bit align the value they passed in. Now we find the first section that it fits in. Well, if that's null, that means we need to just allocate more memory. So we just call that allocate alloc new memory function we created. Alright, so after that, now we can get the size of that one that was returned, because it might be a lot bigger than the size we need. So let's get the difference in the size that we need versus the size of that chunk that got returned. If it's greater than this resize threshold, we're just going to actually separate this into 2 chunks and not just take up this big chunk of memory with a small bit that we need. So we're going to grab say the other size is diff minus the full header size. We set that size for the next chunk. And let's just call this next size, that makes more sense instead of other size. Alright, so now we're going to set the flag mem allocated on our first section, and we're going to return the pointer plus the header size. Now for free, what we first want to do, remember they're going to pass in the pointer that they got, so we need to subtract the header size off it so we can get back the pointer that we actually started from. So if the chunk was mapped, it was not on the heap, it was in the map, so let's just call sys unmap and using the chunk size. And we'll print out some details here. So that one's easy enough. Now, if it's on the heap, first we want to unset the flag mem allocated, so now it's free. So now, if the next chunk is free as well, why don't we just combine them together and make it into one chunk, so that if a larger section needs to be used, they'll have that available to them. So we'll create a new chunk out of that. We'll grab that second chunk, create a new chunk out of this one and the next one, set its size to the addition of those plus the full header size. And now if the next chunk is also past the end of the heap, well then, we can just call sysbreak and actually really deallocate this memory. So we're going to move the breakpoint back. We'll do some actual freeing of this memory, because for right now we've just been setting it to allocate it or not. But now we're actually going to move the amount of memory that the application is using back. And if it's less than the first free, then we'll set the first free pointer to that, which is where we just start iterating. And for print details, actually, I'm not sure we're going to need that. We already have this function up here to print the heap. So let's add some extras in the header here. We'll add malloc and free. And we're going to remember this break function we created that used the sysbreak. We don't want to use that anymore. We'll create an alloc command, which will do the same thing, but it's going to allocate a chunk of memory using our malloc. Still want to use that stir to int. So let's see, we're going to just get rid of all this. We'll say void p equals malloc, given the size that they entered. And just print out the returned pointer. Do we want to do anything else on it? We can print the heap as well. So every time we allocate, we'll print the heap so you can see what it looks like now. And we'll create another one of these for free. So we're creating 2 new commands here, alloc and free. And free, you'll pass in the actual pointer that you want to free. We use this same kind of code that used there. So we're going to say free and then an address. So this address is going to be from that argument that was passed in, and then we're just going to call free on that address. And we'll print out the heap again. So let's see, I think we should be ready to build it now, unless I'm missing something here. Actually, let's bring up a new terminal. First go to the mylib, build that, and install it. Now let's go to lash, make it, and we have an error. Malloc is still used in the load event devices. Oh yeah, if you remember, we had our load event devices that actually calls Malloc, so we can just really change this to malloc. So really, when we start out, we're actually going to have some memory already allocated by this call. So we should have some heap entries right at the start. And let's see, let's print out the heap too before and after that. So right when it starts up, we're going to print out the heap, load this stuff, and then we'll just print it out again. So we'll print it this right before it and right after it, so you can see what was actually created. So now let's install that. And actually, before we reboot here, this function malloc right at the end, I put p plus header flags mask. It should really just be plus header size. So that will cause you a crash if you keep that as is. So let's go back and rebuild that mylib, and now we can reboot. Alright, so we just boot up. Let me resize the screen some. Alright, you can see right off the bat we have all these 80-byte sections allocated, and that's all from those input devices. So let's allocate another, say, 100 bytes. And you see we have size down there is 104, and that's because it 8-bit aligned it, and remember we created a 4K chunk, so that whole next section is free. So you have 3536 as the leftovers as a whole other free section after that one that we allocated. So let's allocate some of that. We'll say 3000. So now we have 104, 3000, and we have 528 left free. So now let's free one of these pointers. Let's do that one that we just did, the 3000 byte section. And now you see that it actually combined it with the one after it and then resized the break, so now we don't have those sections left at the end. And now we can free another one here. Let's see, 64. So I freed this one 80-bit section, you can see, 80-byte section. I'll free another one of those. Now you see it combined those two. Now let's free this one. And now you can see it removed the last one, and now our heap is a lot smaller. And we can just keep doing this, removing sections. I just combined two and it removed them. Now we can allocate another one, let's say 5 million. And if you can see, our heap is still the same. You look at the return pointer, it's way out there. That's because this is used by unmap. So there's our memory mapped pointer way out in the far distance there. And let's see, I got a seg fault when I tried to free it, so something must have went wrong. Let's take another quick look at the code there. It's probably a return that I forgot. This is usually not too hard to debug. So we know it was during freeing a memory mapped section. So if we just pop that back open, look at free right here, is chunk mapped? Yeah, we just got to call return after that. So instead of returning right away, it was going on to also try to delete it as if it were a regular map section. So now let's make install and reboot. And I'm sorry if this is going fast for you. I just wanted to keep this to a reasonable size. Alright, let's just go ahead and allocate a giant chunk again. Alloc 5 million. And you see we got this returned pointer, and it's not on the heap. It's a separate unmap pointer. And this is the same thing that the regular malloc does, but a little more advanced than this. This is, yeah, there you go, free work just fine. So again, I know this was really kind of fast, but I kind of wanted to breeze through the code just to give you a good example without taking, you know, an hour to go through. So I kind of sped it up twice. But you know, this is a good example of a small memory allocator, not as advanced as malloc that's in libc, but it's the same principles that it uses. It uses a headers and a doubly linked list type style and unmap. Actually, I think it uses unmap for everything, but you know, I never really got that deep into it. But this is an example on how you can create your own heap, so you can allocate and free memory pretty efficiently. So this should be a good start to really get going on the rest of the OS that we're creating here. So I hope you enjoyed this video and learned something from it. If you did, again, please like, comment, subscribe, all that stuff. And join our Reddit subreddit if you have more detailed questions. And thanks again for watching.